Hello everyone. It's an honor to be here at NeurIPS' 2024 Muslims in ML workshop, presenting our titled work GREC Knowledge Expansion in Material Science. This work has been accepted to the third Muslims in ML workshop, co-located with NeurIPS 2024. Material science is a field that relies heavily on precise and up-to-date information for innovation. However, when we look at the tools available today, particularly in LLM field, where we can integrate the Retrieval-Augmented Generation, which also known as RAG, we see significant limitations. These models can retrieve outdated or irrelevant spatially information, struggle with hallucination, and fail to provide sufficient interpretability, especially in our domain. Our goal with this research was to overcome these challenges by leveraging the strengths of graph databases and improving retrieval accuracy and contextual understanding. And that's what led to the development of GREG. Okay, let's start by understanding the problem we set out to solve. Current REC approaches, while powerful, rely heavily on unstructured knowledge bases and simple retrieval pipelines. Although there are many advancements right now happening in the RAG field, but still uh, there is a lack of having a proper pipeline. This limits their ability to provide reliable, contextually relevant answers, particularly when dealing with extensive specialized domains like we have right now in material science. For example, traditional systems may return a mix of relevant and marginally useful information, diluting the quality of the response. We identified this gap and realized the potential integrating of graph-based approaches to enhance both the retrieval and generation processes. Our proposed solution is a graph-enhanced retrieve-augmented generation system designed specifically to tackle these issues. The core idea is simple. Instead of relying solely on text chunks, we employ a graph database to store entities. Here we are making the term as MatIDs and their relationships. These entities are extracted from material science documents through advanced entity linking and relation extraction techniques. The graph structure allows us to capture the rich semantic relationships between entities, enabling more precise and context-aware retrieval. Our defining features of GREC is the integration of external knowledge base, especially for this part we are using Wikipedia. Here's how it works. After parsing a document, we identify key entities such as material properties, compositions, and experimental results using our span parser module. These entities are then used as queries to retrieve additional information from the Wikipedia knowledge base. By tapping into the Wikipedia's vast and continuously updated repository, we enrich the graph database with contextually relevant data. These steps ensure that the system is not constrained by static nature of internal data, but remains dynamic and comprehensive. Our pipeline begins with PDF parsing, a critical step in material science where data comes in diverse formats, including text, figures, and tables. We utilized advanced tools like Visual Instruct models for figures and Microsoft's Table Transformer for table data. This ensures that all relevant information is parsed accurately for downstream tasks. We also introduced some agents to validate that our parsing is happening very perfectly or successfully. So here is the overall methods of how we are parsing all the PDF, PowerPoint, and all the text file, and then also figures and tables, and then all the chunking, and then operating all using agents, and then validating the process. Here the span parser identifies key entities, and the passage processor integrates these entities into a coherent graph structure. By connecting their entities with their semantic relationships and supplementing them with Wikipedia derived knowledge, the graph database forms a foundation for highly targeted information retrieval. The span parser is the initial component of G-REX system, designed to extract relevant entities and relationships by comparing semantic similarities. It encodes both the current knowledge base and external passage, such as Wikipedia, into high-dimensional embeddings. The similarity between the query and external passage is computed using a dot product embeddings. The module ranks and retrieves the most relevant passages, ensuring precise and targeted information retrieval for downstream tasks. The passage processor processes the retrieved passages alongside the existing knowledge base, combining them with structured input sequences. It uses transform models to generate contextual embeddings and identify relevant spans within the combined data. By calculating probabilities for start and end tokens of the spans, the module ensures accurate text segmentation. This facilitates robust entity linking, relationship extraction, and integration of knowledge, external knowledge into the system. Here is also the retrieval process from the graph database, where we are using also the LLM, and here we are using the llama index for all the processes. What sets G-REG apart is its ability to balance the accuracy, faithfulness, and relevancy. Unlike traditional REG systems that struggle with limited context windows, G-REG ensures the most critical nodes and relationships are queried from the graph database. This keeps the information concise and relevant, even with the token constraints of current LLM. For instance, when retrieving the yield strength of material at specific temperatures, GeoEd doesn't provide numbers. It contextualizes these values with the information about grain size, thermal effects, and compositions. This is invaluable in material science, where precision is paramount. To evaluate GRAG, we designed a dataset of 10 domain-specific queries covering complex material science topics. Our experiments compared with NaveReg, GraphReg, and GReg on metrics like quietness, faithfulness, and relevancy. The results were striking. GReg improved quietness on scores by 60% compared to the NaveReg and demonstrated superior context relevancy. For example, in a query about the yield strength of an alloy, G provide accurate contextual responses that align closely with the ground truth data. This level of precision highlights the transformation potential of graph and enhanced approaches, particularly with the added depth of Wikipedia integration. So that's our presentation. Thank you all.